So, as I posted on the Facebook page, Pavel very nicely cleaned up the soldering area. Thank you, Pavel. I expect you all to keep it just as clean as it is today. So when you get done soldering, sweep up the remains. Put away the spare hardware, please.
There are usually brushes on every row of the station, so you can just grab a brush.
Yeah, there's brushes there. There's cleanup stuff. It had gotten to the point where you couldn't tell which soldering iron was hooked to which base station. You couldn't actually see the surface of the table anymore. So keep it clean. Any questions about final projects? I2C. One guy had a question about I2C. Yes.
Has anyone gotten I2C working?
Anybody using I2C? Would you like to consult with? So the problem is that you can't get an ACK back from the device. Is that right? So sending out an address, sending out a start condition. The start condition is apparently set. You can see it on the scope. You can see the address going out. It can't tell whether it's ACKing back or not. Any ideas about?
What's the line voltage, the data line voltage?
3.6.
And so after you send out the address, it goes back high? Okay. I was having an issue with that on some chip, but I'm not sure if it wasn't working. And then I went to a different chip and it worked. So
I tried the second accelerometer and same exact thing.
Same accelerometer. Yeah, the second accelerometer didn't work. You can see a little glitch on the data line, like the driver of the Mega 644 turned off and the driver of the chip turned on. See, just a little tiny impulse. So I think that the chip recognized the address and is driving the bus, but the ACK bit doesn't seem to be correct.
I would, if you can get your hands on some other I2C device and try hooking it up and try to see if your system or if you put another I2C thing on there and it doesn't work, that's probably your fault.
Yeah, that's a good point. It's worthwhile trying to see if there's some sort of control. I don't have any I2C devices laying around the lab that I know of. Maybe somebody else does.
Who has used I2C before? Maybe there's some info on their project.
There's two camera projects that have used I2C, and they both use the same code base, which was the TWI master code that I talked about a few lectures ago, which is what you're using, right? That's what you're using?
You changed the port on the I2C master? Okay. That was the only real hang-up that...
The port?
You have to specify the correct port for whatever device you use.
Oh, and it defaults to something other than Mega 644, so it was...
Yeah, you have to set the pins to the port for whatever the data line or clock lines are.
And you did all that, yeah.
Yeah, it's the same way too.
Are you looking at, have you looked at the clock line too? Is that...
Yeah, that's expected. You tried bunch of different frequencies, but we were working at 100 kilohertz, which is well below the maximum.
10 clock pulses came out on the with the. Now I thought there should be 9, and there were 10 clock pulses, but maybe one is needed for the start bit. Yeah, you've exhausted my knowledge. 2 minutes. So, any other questions on projects or hardware? Let me remind you now, it's 2 weeks. 2 weeks until demo time for the Wednesday group. And so it is now time that if things are not going well, you need to come talk. If you have a desperate hang-up, you have a minor problem that you're going to work through, that's all right. But if you have something that is really a showstopper that you can't figure out what to do next with, you need to come talk. Any other comments on final projects? So let's talk about assembly language a little bit. There's a couple of ways of embedding assembly language into a C program. And I don't think anybody is going to write a whole project in assembler. I haven't seen that in several years. The last guy who did that wrote a complete video generation program and generated Pac-Man in assembler because he couldn't afford the C overhead. It's a bewildering chunk of code. And but I don't recommend that. What I recommend is, like any other coding experience, is that you write it in C, and if you need more performance someplace, or you need a set of operations that are just quite hard to do in C, like some bit manipulations, then you write a little chunk of assembler and drop it into the C program. If it is a fairly substantial chunk of code, you might make a function out of it, which is quite easy to do. If it is a less substantial chunk of code, something that needs to execute really fast without the overhead of the function call, then you might use Inline Assembler. That's not so easy to use. It's fast but not easy. The usual trade-off, right? This assembler, the machine architecture, the instruction set architecture, is more or less RISC-like. There's 32 8-bit registers. It has a set of instructions that look a lot like most RISC machines. There are, however, a couple of oddities about it. All of the arithmetic instructions work on all the registers. So an add works on any register pair. It's a two argument machine, which means if you say add R1, R3, it takes the value in R3, adds it to R1, and puts it back in R1. So it's a 2-argument machine rather than a 3-argument machine. But not all of the instructions work with all of the registers. For instance, add works with every register, but add immediate only works. So this would take a register and then a value, 8-bit value, and add immediate only works on registers R16 through R31. And so you'll get an obscure error, something like register value not allowed, or something if you use R15. All of the immediates, all of the immediate instructions, or immediate, and immediate, add immediate, load immediate, all require R16 through R31. There's some other instructions which use very restricted sets of registers. I think that multiply signed only allows you to use 4 registers as inputs, or maybe 6 registers as inputs. Also, R0 on this machine has no particular special value. It is not locked to 0. R0 and R1 are always where the result of an 8x8 multiply end up. R1 being the high byte, R0 being the low byte. If you do a multiply in assembly language, therefore you will have changed R1, but the compiler enforces the notion that R1 should always be 0 and depends upon it being 0. Therefore, at the end of your code, before you go back to C, you have to set R1 back to 0. if you were to call a function so you have some function, let's call it int A, int B, then an int function of int A, int B, when the function linkage is complete and you are now executing in the function, the first parameter is in register R25, R24. R25 being the high byte, R24 being the low byte. The second parameter is in R23, R22. And so on until you get down to R16, and then after that the parameters go on the stack. I guess I would have preferred a uniform model, whether they're either on the stack or in registers, but I didn't design the compiler. The return value, if it's an int, is always in R25, R24. If it is a byte value, I'm pretty sure it's in R24, sign extended into R25. Yes?
I've tried at least when you pass in the parameter. If it's a byte, it's put in R24.
It's in R24, yes.
When you pass it in, so I guess when you
it assumes the compiler is sort of defaults to ints, or if you want prefer, it's byte aligned on the even registers. So the output will be in R24, sign extended into R25. If you pass in a long, it's going to be in R25, R24, R23, and R22. In that order, high to low. So parameters are like that. Safe registers that you can use anytime you are in an assembly language routine. Safe registers are R18 through R27 and R30 through R31. So C saves those registers for you. If you're doing inline assembler, if you're putting code in line, obviously the registers have not been saved for you. But if you drop into a function, these registers have been saved for you. What happened to R28, R29? Turns out that R28, R29 register pair is used by the hardware as a stack pointer. So you dare not use that. Unless, of course, you push it on the stack. Yeah, it works. So then let's write a function. And I wanted to make some really fast fixed point arithmetic, so I started by writing an assembler function which did a 8-8 multiply, and it was faster than the built-in multiply because I totally ignored the top byte and the bottom byte because they were outside the precision range. And the first pass was a function, but it wasn't any faster really than the C because of the function call overhead. So then I recoded it as an inline. So I'll do both of those. So what I'm going to code is int multfix int A int B. And this is an assembler comment. This whole piece of code is going to be in a file called mult.capital-S. Capital S. Capital S is the file type that the assembler recognizes and that the linker recognizes in WinAVR to automatically link your code together. So if you want it to work, it's got to be an uppercase S. The first thing in the file is going to be a command to the linker to make the entry point of the function a global. So that forces multfix to be a global available to the linker, and then we just define a symbol multfix, which is now the entry point. Now there's one other small detail. I mentioned that multiply is picky. Multiply requires that only registers 20 through 23 be used for a source if you're doing a MUL. So we needed to move one of the parameters is already in R23, R22. B is, but A is in the wrong spot for the multiply command, and so we need to first move that to the correct spot. So we're going to do a move to R20 from R24 and a move to R21 from R25. So that moves the first parameter, the A parameter, into the correct position for the multiply. And by the way, clears out R24 and R25 for the return parameter. And because we're going to have to do several multiplies and add them together, we need an accumulator register to do finish the multiply, to do the multi-byte multiply. And R24, R25 is going to be our accumulator, which also happens to be where the output is going to be. Then we do a mul signed. So this is a signed multiply of R23 and R21. Those are the high order bytes. The high order bytes carry the sign, SIGN. So we have to do a signed multiply. So let's write this out. We're doing a signed multiply of an 8 times an 8. So we're going to get a result that looks like this, with this being overflow and this byte being underflow. So we only need the middle 2 bytes, which means that we do not need the high byte of the high multiply. So we only need to move the result of this multiply. These are the 2 high bytes. We take the low byte of the high multiply and move it into R25. So R0 after the multiply, R0 has the value of the low byte. We move it into R25. Then we do an unsigned multiply. An unsigned multiply of the low bytes and move that into R24. But in this case, we only need the high byte because the low byte of the low multiply must underflow. So we only need to move R1. The high byte of the multiply result gets moved to the low byte of the result. Yeah. Okay. Then we have to do, so now we've multiplied this byte times this byte and this type times this byte. Now we have to do this byte times this byte and this type byte times that byte. So now we do a multiply signed times unsigned. So one of the parameters, one of the inputs will be a signed value, the other input will be an unsigned value. So we're going to do a multiply signed unsigned of R23, that's the signed byte, times R20, the unsigned byte of the other input. And now we have to add the output of the multiply R0 to R24 because we're accumulating the result. And then we have to do an add with carry R25 and R1. We have to do the carry because this add may have generated a carry or may not have, but we have to account for it on the high order byte. And then we just do another mul sign unsigned, this time of R21 times R22. Do an add R24, R0, add with carry to R25 of R1 to get the other result. And then all we have to do after that is to clear R1. That's for the C compiler. Have to clear R1 and return. Do an RET. Because I chose R24, R25 to be my multiply accumulator, the result is automatically in the correct place for the return. Because R24, R25 is the return for an integer result. So how many cycles does this take? A move is 1 cycle. A multiply is 2 cycles. An add is 1 cycle. So we have, that's supposed to be a move, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 cycles for the basic multiply, which is pretty good, plus the return, which is 2 cycles. But what kills you is that the function setup is several cycles. Dozen cycles. Any questions on this? I'm going through this kind of fast. I assume that you've seen assembler before. Someplace or another. Yeah?
Why you clear R1 but not R0?
You just, because the assembler, because the compiler assumes that R1 is 0. I didn't write it. Why didn't they use R0? I have no idea.
So does that mean no matter, I mean, in whatever case we use R1,
You must zero
I
it.
must zero it?
Yes, must zero it. Yes. So the only time you can not avoid using R1 is if you do a multiply. And since that's what I was doing here, I have to clear it. Otherwise, I would have chosen another register to avoid one instruction.
So if you were to write entirely in assembly code, would you be able to use R1?
Sure. If you write entirely in assembly, you can do anything you want to the registers. However, I don't recommend that because if you write completely in assembly, then you have to do some bookkeeping that you're probably not used to. One is you must set up the stack pointer by hand because the CPU does not do it for you. And then you must define all the interrupt vectors by hand if you use them. That's not hard, but you got to do it. So, looks like any other assembler, kinda. It's not easy or hard, it's just assembler. The only time assembler gets completely out of control is if you have big nested if-then-else conditions. And you have to convert those into jumps and computed branches, and that's just horrible. Nobody writes big nested if-then-else's in assembler if they can possibly help it. So now, to save time, then I converted this to inline. And the reason that inline is uglier is that you don't know where anything is. I mean, how do you know whether a variable happens to be in memory or happens to be temporarily in a register or on the stack or wherever it happens to be? So you need a way to force C to identify where the variables are going to start and where they're going to end. You want them to be compatible with the symbols that are defined in C. And you want to be able to allow the optimizer to do as much with your code as you possibly can. So you want to give it general description of registers without specifying registers. So for instance, there's a constraint that you can say, I don't care what register you use for this as long as it's R16 through R31. Or I don't care what register you use as long as it's compatible with a multiply. And there's about 20 different constraints that are defined in GCC for this particular architecture that allow you to specify the kind of register you want without specifying the register, the exact register. So the optimizer can go crazy on it. So let's do a pound define of a symbol multifix a comma b. And we're going to use the backslash here. That means continue. To continue on the next line. So the next line is going to be round bracket, curly bracket, backslash. The next line is going to be, we're going to identify some variables. Now, I'm not quite sure why I did this, but we'll do that. Value 1 equals A, value 2 equals B. Semicolon, backslash. Then there's this really ugly construction, which is underscore, underscore, asm, underscore, 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 volatile with a space in there. All right. So it's underscore underscore ASM underscore underscore space underscore underscore volatile underscore underscore. I didn't think it up. In fact, the only way I could figure out how to do this was, as I said, I think I said before, was to find an example that was fairly close to what I wanted to do and copy it. Now this is There is no separate file. This is not in the .s file. This is going to be directly in the C program. And what we're going to put after this, I'm just going to move over here so I can start nice and high on the board. We have to quote now the assembler commands. So we're going to do a multiply S of the parameters, but we want to make this as flexible as possible. It turns out that the return parameter, the value that this returns, is going to be referred to as parameter 0. This is parameter 1, and this is parameter 2. So what we're going to do here is we're going to say that we're going to do a mult S of percent B1 percent B2 backslash n backslash t, because that's what the assembler requires. Now what this means is use the upper byte. The B byte is the upper byte of parameter 1 and multiply it times the upper byte of parameter 2. And so these are kind of meta instructions to the that are going to be filled in by the compiler before the assembler is called. They're going to be filled in with real register values. Then do a move percent B0. That's the output parameter, the high byte of the output parameter, from R0 back n back t backslash. Now we're going to multiply, unsigned of course, A1 times percent A2. That says take the lower bytes, the A bytes are the lower bytes of parameter 1 and parameter 2, multiply them together. And then move percent A0, move percent A0 R1 backslash n backslash t. You notice we haven't said here you gotta use R24, R25. Haven't said anything about what registers have to be used. The compiler gets to choose, as long as it's someplace that you can actually do the move to, which is any register. I think you can see the pattern for the rest of this. I'm not going to write this all out unless you want to see it. But after a while here, after doing a bunch of adds of various kinds, we get down to a clear R1. You can use the name of a register directly. That forces it to be used. In this case, you don't want to clear some register. You want to clear R1. Then, after this, you have to tell the assembler, the inline assembler, what all these parameters mean. And these are referred to as constraints, and this is what bent my brain. So the first constraint is an output constraint, and we're going to say that the constraint is, it's equal ampersand, which means treat it as output only, and use a register of type D. Oh my God. So you look in the table, and you find that a register of type D is R16 through R31. And we're going to identify this with the variable product. which we defined up over there. That needs a quote there. Then there's going to be an input constraint which says that we want to use a variable of type A for value 1. And a type A is simple upper register R16 to R23. So this is R16 to R23. Simple register means not a register pair. And we need to make another type A constraint of val 2. And then we close the inner parentheses after the volatile. Then we invoke the name product, which returns now product as the value of this. Then we do a curly bracket, no semicolon. Now this is just plain ugly. I mean, it's just, there's no way out. This is a homely chunk of code. But it executes in 17 cycles.
Is this a macro here?
It is a macro.
Okay.
It is exactly an inline macro whose body happens to be an assembler rather than C. Mostly an assembler. And by using this hideous construction, this underscore stuff, it clues the compiler in that there's going to have to be some interpretation done to this code before the assembler is called. So all of these registers that are hinted at as R16 through R31 or R16 through R23 have to be replaced with actual register values for the assembler. That's kind of cool, because it means now that you're an unnamed co-conspirator for the compiler that's figuring out how to arrange these registers to optimize the compilation process, to optimize execution.
And the way the C knows that prod is the return for the macro is you
I reference it there, yes.
Okay, so that's how it makes the
Right. It makes the return value.
And so I know there's also something like with underscore ASM without the volatile. What's the difference?
Well, I've never used it without volatile. You don't want C to optimize it away, and this guarantees that you're not going to optimize it. The various constraints are, listen to this kind of constraints. You have your A, which is your simple upper registers R16 through R23. You have B, these are pointer register pairs, and they take on the value Y or Z. Y happens to be R28, R29, and Z happens to be R30, R31. There's E, which is pointer register pairs X, Y, or Z. There's Q, which is the stack pointer register. So you can hint it as Q. R is any register. T is temporary register, R0. W is special upper register pairs, 24, 26, 28, and 30. Because there are a few instructions that are double byte operators, like increment double. G is a floating point constant. I is a 6-bit positive integer constant between 0 and 63. Huh. What's that for? That's for I/O registers. That's for specifying I/O registers. K is an integer constant. L is an integer constant. L is the lower registers R0 through R15. And then there's some really obscure stuff I'm not even going to mention. So the exercise here is to figure out what each instruction requires and come up with the constraints necessary to satisfy that instruction. And the errors you get back are completely incomprehensible. Because now it is the assembler throws an error which is the result of C interpreting what you meant by your constraints.
Well, the compiler assumes you know what's up.
The compiler assumes that the operator is competent. That being said, this is not so hard to use most of the time, if it is, particularly for simple stuff. If you want to do a CLI, you want to do a short I/O instruction sequence, you want to toggle a bit back and forth, it's relatively simple to do that because you're not using any registers other than the I/O register. You toggle a bit in the I/O register, all you need is the I/O register name, and a CBI or SBI, clear bit or set bit. So there's some things that are quite easy to do. There's some things like this where you're doing all kinds of weird constraints that get pretty baroque. But it is fast when it compiles. So the reason for doing this was I needed a fast multiply so I could write fast digital filters. And by using a fast multiply with 8 filters, with fixed point filters, you can execute about 10 4-pole infinite impulse response filters at 8 kilohertz sample rate in real time. So that's not bad. You do quite a bit of filtering. And I wrote infinite impulse response filters for this, in case anybody wants to do filtering. I wrote cascaded integrator comb filters for downsampling, for multi-rate filters. I wrote an FFT, discrete cosine transform, and fast Walsh transform, because I like Walsh transforms. That breaks things down into orthogonal square waves rather than orthogonal sine waves. And there's, of course, some of the music synthesis stuff. You're welcome to use any of that stuff if you need it for a final project. I'll be happy to consult on assembly language. At this point, there's no other outstanding requests for lectures that I know of. And so, yes?
Can we talk about low power?
Low power. Oh, low power. I could talk. Yeah, I could talk some about low power. So let's take a vote here. I can talk to the group about low power. I can talk to you about low power. Either way. As a group, would you rather hear about low power operation, or would you rather I stop lecturing and go to the lab every day? Okay, low power. Stop lecturing. Well, I guess we know the answer on that one. I'll talk to you in the lab about low power. I'll talk to anybody who wants about low power, but it looks like this. Okay, then this is the last lecture. This is now Wednesday, is that right? Yes, Wednesday. So Friday, we'll be in the lab all day from 9 a.m. till 4:30. Yeah. And so thank you. It's been fun.